Hello students, today we will discuss about the Gauss theorem. There are some certain elements in the Gauss theorem that we need to discuss. First one is area vector. We know that we have two terms, one is scalar and second is vector. And according to the definition of scalar quantity, those quantities which are having only magnitude, not direction, so those are scalar. So area is a scalar quantity because it is not having the direction, and those quantities which are having a magnitude and directions, those are treated as vector quantity. But now we are treating here area as vector quantity. Why? Because in some cases only magnitude is not sufficient. Only magnitude is not sufficient. Orientation of that thing also play an important role. For example, area. Why? Suppose we have a flow of water in this direction, okay, and we have a ring, this type of ring. We are keeping this ring in the flow of water and we want to calculate how much amount of water is passing through the ring. It depends on the orientation of the ring. If we are keeping this ring perpendicular to the flow of the water, then maximum amount of water will flow through ring. Why? Because the surface of the ring is in the direction parallel to the flow of water, and if we keep this ring in this way facing towards this side, so in that case minimum water, or you can say negligible water will flow, right? Why? Because the plane of this ring is in the direction of flow. So for now we conclude that orientation plays an important role for describing the amount of water. This is the surface area of the ring, and if we give a normal to this, suppose this is the surface area, ds is the surface area, and we are keeping a normal to this surface area, then this will become a vector quantity. So ds is equals to ds into n vector, n cap. Why? This vector, this is a unit vector and is always used to give the direction. So that's why we have to use the area as a vector quantity for Gauss theorem. After area vector, we are going to discuss with the Gauss theorem. Gauss theorem and electric flux are related to each other. Electric flux, the next element of Gauss theorem. First element was area vector, second element is electric flux. Electric flux, we will represent this as phi E. What is electric flux? Electric flux means the number of electric field lines that are passing through a given area vector. Okay, the number of electric field lines that are passing through a given area vector, so that will give us electric flux. So if I take one example, these are the electric field lines and I am having one surface area ds with normal. This is the perpendicular, so this is our vector area ds. In case 1, when theta is equals to 0 degree, now this theta is 0 degree means between the electric field lines and the normal. Theta will be in between the electric field lines and the normal, right? So this is surface area and this is the normal. If I keep the surface area or the plane perpendicular to the, I am repeating the words, I am keeping this plane perpendicular to the electric field lines, but normal of this plane is making an angle 0 degree with the electric field lines, right? So perpendicular doesn't mean theta equals to 90 degree here. Theta we have to check with the direction of normal and with the direction of electric field lines. The angle of plane and the electric field line is a different thing. I am keeping the surface area like this, and now the normal is in the direction of electric field, so our angle will be 0 degree. So there is formula for electric flux. Electric flux is given by E dot ds. So we can write E ds cos theta. After bringing the dot product, now angle is 0 degree. So phi E will be E into ds. That will be maximum. This is the first case. In the second case, when I keep the surface area in this way, okay, now the direction of normal of the plane is perpendicular to the direction of electric field. Electric field is going from this direction to that direction, and normal is in this direction, so theta will be 90 degree. Case 2, theta is equals to 90 degree. So for that thing, these are the electric field lines and I am keeping the surface here, and this is the direction perpendicularly outward, that is perpendicularly outward, right? This is n. So electric flux will be vector E dot vector ds. So E ds cos 90 degree. So cos 90 gives us 0, so we will get electric flux 0. So no electric field line will pass when our surface will be like this. If we keep this like this, then maximum number of electric field line can pass through this. So that is the electric flux. Okay, next we will come to Gauss theorem. What is the Gauss theorem? We have a charge plus q and it is having its field up to this point R. If we want to calculate the electric flux at this point, say at this point, so the distance of that point will be let small r. Okay, so there will be a Gaussian surface and that surface must be closed. This is the first condition for any Gaussian surface. Gaussian surface is an imaginary surface within which we can calculate the electric flux. What is Gaussian surface? It is an imaginary surface within which we can calculate the electric flux. Okay, so and this is the normal. In same direction, this is the normal. I am taking ds. Okay, a smaller part. So normal is like perpendicular. Okay, perpendicular to the surface. Now we have to calculate the electric flux over the given Gaussian surface. So what will be that? According to Gauss theorem, total electric flux over a given closed surface, you can say the Gaussian surface, is always equal to 1 by epsilon naught times the total charge present in that Gaussian surface. Okay, so phi E electric flux over a given closed surface, this is the closed surface, Gaussian surface, is always equal to E dot ds, integration for a closed surface. So phi is equals to E dot ds for a integration of a closed surface, that is equals to 1 by epsilon naught into total charge present within the Gaussian surface. So what is the total charge? Q. That is the Gauss theorem. If 5Q is there, then flux will be 1 by epsilon into 5Q. Okay, this is for example. So that means the total charge present within the Gaussian surface with the multiplication of 1 by epsilon naught, that will give us the electric flux. So this is the important topic for the board. There are 5 applications of the Gauss theorem. What are the importance of the Gauss theorem? We can calculate the electric field by using the Gauss theorem. If we use this formula and this formula, then we can calculate E if we are provided with the Gaussian surface. So this is the importance of the Gauss theorem. So we can calculate electric field around a given Gaussian surface. For a point charge, this is point charge plus Q. For a point charge, Gaussian surface will be spherical in nature. And for a linear charged conductor, suppose plus Q charge is uniformly distributed, then for this kind of conductor, Gaussian surface will be cylindrical in nature. Okay, so this is the